Now we come to the second part of the student presentations. We had 2 yesterday, and we have 2 more today. And it's my pleasure to introduce as our first student speaker is John Fyffe. He's a PhD candidate advised by Chris Edwards, who we heard from earlier this afternoon, in the Department of Mechanical Engineering here at Stanford. His research in the Advanced Energy Systems Lab focuses on combining electrochemical energy conversion with the more traditional combustion systems, with the goal of achieving 70% efficiency at small scale. So John received his BA in Mechanical Engineering from the University of Texas at Austin, and he will be talking today on mixed combustion electrochemical energy conversion for high efficiency small scale engines.
Thank you. So it was nice. Chris talked a little bit earlier, so those of you who saw his presentation, that'll be helpful as we go through some of the stuff that I'm doing. So thanks, Chris. Okay, so today, like he already mentioned, we're going to be talking about our research into a new strategy using a mixed combustion and electrochemical energy conversion method to try to reach higher efficiencies. And so we're going to be specifically targeting smaller scale, whether that's transportation or distributed generation. So what that means is when you're thinking the technologies I'm using, think small scale turbines, so lower turbine inlet temperatures, all of those constraints, not grid scale devices. And so why do we want better chemical engines? Obviously, we talk a lot about wind and solar, but if you look at where energy comes from in the world, we're still at over 90% coming from some form of chemical fuel, and 80% of that is currently from fossil fuel uses. But a chemical engine could use a fuel that is bio-derived or even created using renewable energy, if you'd like, in the future. And so what do I mean by better energy systems? Well, today, that's going to mean more efficient. It could mean cheaper, it could mean lower emissions, but today we're going to just be talking about efficiency. And so if you look at the efficiency of systems over time, you'll notice about 100 years ago we were very inefficient. We had steam engines, and then technology developed, the efficiency improved, and then we had a step change as we shifted architectures. So that moved to steam turbines, and then gas turbine combined cycles, which is where we sit now. That's the current state of the art for natural gas-based systems. It's about 60% efficiency. And for coal, we have about 50% in the best case scenario. And so what we do in our lab is to try to figure out what are the things that we can do, the devices that we can use, the architectures we can develop to push past into the next energy system architecture. So what is this next line going to look at? And again, specifically, I'll be looking at what can we do on a smaller scale using the devices we have and the constraints that are currently in place. And so why are we using combustion and electrochemical energy conversion strategy? Well, Chris already talked a lot about engines and how they're very power dense. They accept a wide range of fuels, so it's a good starting point. And so let's look at an internal combustion engine. This is an energy analysis of an internal combustion engine. You have work that you can extract from your engine, so that's the blue bar. In this case, it's about 42% efficient. You also have some exhaust that's leaving the system. It's typically high temperature. That has some energy as well. And then you also have heat transfer, and that heat transfers to the walls, the piston, and the head, as Chris mentioned before. But another thing we can do besides just doing energy analysis of an engine is we can use an exergy analysis of the engine. And as Adam talked about earlier, exergy is the useful part of your resource, right? So it's the useful energy, the maximum amount of work you could extract from a resource. So it's a slightly different thermodynamic quantity. And this is an exergy analysis of an engine. And again, you'll see the work is about 42%. You still have the exhaust losses and the heat transfer losses, but you notice that big red bar that shows up on the top. And that is the exergy that you destroyed during the combustion event. It's not because you made hot gases and it transferred heat to the walls. It's literally from the process of converting your fuel reactants to the products of CO2 and water and your other minor species. So that's pretty bad. And so Chris mentioned the research that was previously done in our lab to try to make the most efficient internal combustion engine we could with the means that we already know and like technologies that we have available to us. So our goal here is to make this blue box bigger by making these other boxes smaller. It's a pretty simple approach when you break it down like this, which is nice. And so what we've done before is we reduced the heat transfer. So the yellow box, the heat transfer loss, got smaller, but then our green bar, the exhaust box, got bigger. Why is that? Our exhaust got hotter, right? So now we're just transferring hotter exhaust out into the environment. But we know that we can expand that through a gas turbine. We could overexpand our cylinder. And that would actually then improve our efficiency up to almost 50%. You can see our green bar is still pretty big. That's pretty hot gases still. We can do a bottoming cycle. And this puts us right around 60%. And this is kind of where we decided we've kind of hit the limit. And you'll notice that's because we have this big red bar that didn't really change over the course of all of these technological improvements, making it more of a combined cycle system. We still have this very large red box that's kind of offensive, and we want to reduce that somehow. And so one way you can do that is to use a fuel cell. A fuel cell takes hydrogen, typically, into your fuel cell and reacts it with oxygen through an electrochemical means. So you're not combusting it. It is a more restrained reaction. You still have the same kind of breakdown if you do an exergy analysis of it. You have some work that would come out of your fuel cell in the form of electricity. You would still have exhaust coming out of your fuel cell. And typically, most fuel cells cannot react all of their fuel, so you will have some remaining hydrogen coming out, which has high exergy value. So your exhaust, as you can see on the right, your exhaust exergy is quite large in this case. You're also going to have heat transfer out of your fuel cell. It's an exothermic reaction. And the most important thing to notice, and the reason why we are looking into fuel cells to build combined cycles, is our red bar. Our destruction term from the chemical reaction is very small. And so our efficiency might be 30%. You could design a system that's 40%. But the important part is that you're only destroying a fraction of your exergy, maybe 5% or less. And then the rest is transferred out of your system in the form of exhaust and heat transfer. And so if you don't do anything with those transfers, it's destroyed, right? If you just heat up like some cooling water and then dump that into the river, it's lost. If you don't do anything with your exhaust, that exergy is lost. But we can build a system around it and take advantage of these transfers. And so the important part here to compare against the engine is that the destruction term is small. We want to take use of the fact that it can efficiently convert chemical exergy into work while destroying very little exergy. And so that's what we're going to do. But like I said, most fuel cells require hydrogen. We don't have a hydrogen resource available, unfortunately, and so we have to produce it. Typically, you can use steam methane reforming to do that. There's many other ways you could do it. You could electrolyze things. But what we're going to do is we're going to use an engine that we know is very efficient at producing work, has very power-dense operation, and it can accept a wide range of fuel. So we're going to use an engine as a fuel reformer. And so instead of injecting the correct amount of fuel that would burn all of the fuel with all of the air that's in the engine already, we're going to put in about twice as much, roughly, fuel as normal. And what's going to happen? Well, you're going to partially combust your fuel. It's going to still be exothermic. And that reaction is going to essentially crack whatever fuel you put in there and produce a syngas. So it's going to be a combination of hydrogen, carbon monoxide, and other products. And it's going to be hot, which is perfect for us. So now we can pass that hot exhaust gas to a fuel cell. And here, just so you, for your reference, is an exergy analysis of such an engine. And you can see that we're not getting very much work out of our engine. That's as expected. We put a bunch of fuel in, and we didn't burn nearly all of it. But you'll also notice that our combustion destruction term, that big red box, got much smaller, by about a factor of 2. So we successfully didn't destroy this exergy, this 20% that we're used to, by doing a full combustion process. And you'll notice that most of our exergy is now in the form of our exhaust. So now I'm using that word kind of in jest because it's really high temperature hydrogen containing gas. It's more of a fuel stream. So what happens when we build this system? We're going to take a jumping off point of that system that I talked about earlier, where we had an engine with low heat rejection, and we put turbo compounding on it, and we're going to use that as a base case. And we're going to say, okay, this is what we're comparing against, and this is what we need to kind of beat to see if we're actually going to have any luck with our strategy. And so this is what our system looks like when we had a first pass of this modeling case. And you'll notice that our destruction bar, that red on the top, is now only about 6%. Okay, so that's much lower than about 17% that we had before. But that's not the only thing you need to compare with. So we need to add up all of the reaction-related losses in our system to see if that is less than that 17%. Because if it's not, the strategy didn't really help us, right? Our goal was to reduce that reaction-related loss from 17 to something smaller so we could push past 60%. And so what happens is you look at it, that 6.4% is combustion, and then you have about 2% due to just your fuel cell destruction that I was talking about earlier, and you have another couple of percent that's lost in the fuel reforming process. So you can add some fuel downstream to the fuel cell, and the fuel cell will internally reform it. You could do it upstream, adds another point or two. But the important point is that now, if you add all those terms up, it's only at 11%. So we cut off about 6 percentage points. We reduced it by almost a half. And so now we can say, okay, that worked. We reduced that red bar. We reduced the reaction losses. And now let's proceed. Let's again go through this process of targeting the biggest losses and see where we could push this system, see how efficient we could make it. And the first thing that's easy to go after, that we have plenty of technologies and know how to do, is go after the heat transfer, right? We have hot, high temperature exhaust gases. We can add a steam bottoming cycle. And now we're up over 60%. We're at 63.5%. So this is over 65% LHV system efficiency. And this is using small scale technology constraints. Another thing we're thinking about is, where can we push this? How high can we go? So currently, this system that I'm showing you here has roughly equal splits of work production from your fuel cell, from your engine, and from your turbines, so your steam turbine and your gas turbines. But what if we push more of the energy conversion, the fuel conversion, to the fuel cell, just to see what happens? So we added more fuel downstream and shifted the work ratio to about 10 times the amount of work out of your fuel cell as the engine. And that bumped it up to about 69% exergy efficiency. So this is now over 70% LHV efficiency. And so in summary, again, our goal in the beginning was to see if we could reduce that combustion efficiency, the reaction-related losses, to push past 60% and maybe even reach 70% efficiency by using a mixed combustion and electrochemical energy conversion process. And we've shown that it is possible. One major thing that you'll notice is we kept adding these steam bottoming cycles. There's turbo compounding. There's a lot of thermal exergy in these systems because you're using high temperature fuel cells. You're using low heat rejection engines. And so managing these thermal exergy transfers in your system is critical. And that was something that Chris mentioned earlier, was talking about thermochemical recuperation, something that we're going to be exploring next. And so this is a very critical piece of the pie. And so really digging into, okay, are all of these thermal exergy transfers efficient and being done in the best way is kind of what we're focusing on now. And our preliminary results indicate that we can get over 70% LHV efficiency if we push this with relatively ambitious but not unrealistic parameters. And these are all using small-scale technological constraints by employing this mixed combustion electrochemical strategy. I'd like to acknowledge my colleagues that are working on the same project. So Mark Donahue, who had the poster yesterday that I think quite a bit of you talked to, and also Carol Ragabudo, my advisor Chris Edwards, and then everybody else in my lab who's great, and GCEP for their funding and support. And with that, I'd like to open it up for any discussion.
Efficiency compared to the 70% that you said?
Sure. So that system is 69% efficient. So we are 31% away from the thermodynamic limit, which is 100% exergy efficiency. So I know that sounds kind of silly, but there's no technical, other than just entropy, right? 100% is the definition of exergy efficiency, right? It's the maximum amount of work you could extract from a resource. So getting there, right, is probably impossible, but that's the limit. And so we're trying to push higher and higher.
So I must be missing something. See, you're having now two engines in the way you're describing this as working, an electric engine and your internal combustion engine?
So there will be electric generators. So the fuel cell will produce electric work, and then the engine and the turbines you could connect to electric generators.
If you were just using the electricity. But I mean, if
Right.
you were using it as motion. But why not just use a fuel cell?
That's a good question. So there's a couple of reasons to go after this kind of combined system. One reason is you have basically the engine acting as a fuel reformer. So if you don't have hydrogen to start with, then the engine is essentially functioning as your hydrogen generator while also producing work and increasing the temperature of that hydrogen stream. You can do that in other means. You can use steam reforming or other devices. But that's one reason. The other reason is you have somewhat of a synergistic effect of it is producing work. It is also potentially more rampable. So if you did have it in a car or even if you're doing distributed generation, fuel cells can't follow load clearly nearly as well. So you have that benefit. It's a side benefit, but something that we've thought about, if that helps. Thank you.